Assalamualaikum warahmatullahi wabarakatuh. Okay, now we continue our new chapter, okay, non-uniform flow in open channel part A. Okay, at the end of this chapter, students should be able to analyze the characteristic of hydraulic jump, rapidly varied flow based on momentum equation. Okay, and second, analyze the characteristic of gradually varied flow. Okay, so we have learned the momentum equation in fluid mechanics and also the hydraulic, okay, based on the chapter 1, chapter 2 and chapter 3, okay, for uniform flow and so on. So now we continue for hydraulic jump, rapidly varied flow and gradually varied flow. Okay, rapidly varied flow, okay, occurs when the depth of flow change rapidly within short distance, okay, especially as hydraulic jump here. So when we look at the figure here, okay, from the location 1 here to the location 2 here, so based on the 1 here is y1 is the depth 1 is supercritical, and then when the hydraulic jump is occur here, so the have the yc here, y critical, okay, flow critical, flow depth critical depth, and the y2 is subcritical. So hydraulic jump occurs when supercritical flow change suddenly to subcritical flow within a short distance. So you can explain the definition of the hydraulic jump, and you can also sketch, okay, when your final have the question that to define the hydraulic jump or explain the hydraulic jump and sketch. So you can sketch and also you define the hydraulic jump. Okay, hydraulic jump only occurs if the upstream flow is supercritical, when y1 is less than y critical and the downstream flow becomes subcritical, okay, when y2 more than yc and more than y1, okay. So y1 is depth of flow just before the jump, okay, y2 is the depth of flow just after the jump. Y1 and y2 are known as conjugate depth, so we just know that y1 and y2 is a conjugate depth. Okay, this is the example here based on the hydraulic jump in laboratory flow. Okay, when the water flow from this direction, okay, with this arrow, blue arrow here, okay, and then with the spillway or the weir here, so have the flow is occur, get the hydraulic jump here. So this is the hydraulic jump. Okay, this part is called the hydraulic jump. Okay, so this is the hydraulic jump. Okay, and they have the y1 here and yc at the hydraulic jump and the y2 here. Okay, so this is, we get the y1. Okay, so we get the y1 here. Okay, this is hydraulic jump and we get the y1 here and y2 here. 1 2 y, this is yc and this is y2. Okay, so this is occur in hydraulic jump laboratory flow. Okay, and this is also in the real life here, hydraulic jump at the toe of spillway in Brazil dam. Okay, so this is based on, this is the hydraulic jump. Okay, so and also the downstream of sluice gate here, so they have the hydraulic jump here based on the hydraulic jump here in Canal Turkey. Okay, and also the wave hitting seawall in Depot Bay in US. Okay, when the flow and the wave based on the direct flow here, so they have the hydraulic jump here. Okay, so this is based on the real situation for hydraulic jump. Okay, and also the here, okay, surge wave due to fast flowing flood in China here. Okay, so this is the hydraulic jump occurs here. Okay, when from supercritical to subcritical flow. Okay, so this occur the hydraulic jump. Okay, application of hydraulic jump. Okay, so this application of hydraulic jump is as an energy dissipator for reduced velocity and prevent erosion. Okay, raise the water level for irrigation or water distribution purposes. So increase weight on apron by raising the depth of water to prevent uplift pressure. Mix chemical substance. Okay, the application of hydraulic jump is as a mixer. Okay, chemical substance in water treatment process and acceleration of flow for increase the DO, dissolved oxygen in water treatment process. So this is the application of hydraulic jump. Okay, so type of jump. So based on the Froude number before the jump, Froude number 1 is 1 to 1.7 is undulate jump. Okay, Froude number between 1.7 to 2.5 is the weak jump here. 2.5 to 4.5 is oscillating jump. 4.5 to 9 is steady jump. And Froude number more than 9 is strong jump. So this is the type of jump based on the Froude number. Okay, so this is the sketch. You can sketch the types of the jump. Undulate jump, okay, weak jump, oscillating jump, steady jump, and strong jump. Okay, the strong jump is based on the energy dissipation up to 85%. Energy dissipation is between 45% to 70%. This is based on the steady jump. Okay, and the Froude number based on 1 to 6, so this is undulate jump. Okay, so momentum equation. So we use the momentum equation to use the frictional flat bed within a rectangular channel. So we use the using the force here momentum equation based on the force at the y1 here, okay, and the force at the hydraulic jump here and the y2 here. So we have F1 here, F2 here. Actually this is F2. Okay, so this is F2. Okay, just correct that this is F2. Okay, and F3 and the F4 here. So we use the friction loss flat bed here, the momentum equation. So we use the here. Okay, F1, okay, minus by F2, okay, minus by F3 and plus the F4 is equal to density times by the Q V2 minus by density times by the Q V1 here. So the since friction is equal to 0, so F3 is equal to the 0. Okay, flat bed F4 is sine theta here because based on this hydraulic jump, so we have the friction here. Okay, so now based on the F1 minus by F2, we get this formula. So and you just convert to this. Okay, okay, and then convert to from this formula. So you just convert to this here. Okay, dividing by density times by the G times by the B here. So you just convert to this part here. Okay, when V1 is equal to Q over Y1 and the V2 is a Q discharge per unit weight is divided by the Y2 here. So until you get this formula and this formula, and then the last you get this formula. Okay, okay, example 1 here. Okay, activity 4.1 here. So using the momentum force equation, draw the specific force curve if a hydraulic jump occurs within a rectangular channel with the discharge per unit weight is 25 feet cubic per second. So this is based on the feet here. Okay, using the US unit. So given Q is flows in a rectangular channel. So specific force is given as this value here. Okay, based on the momentum flux and hydrostatic pressure. Okay, so we have learned the momentum and the hydrostatic pressure in fluid mechanics. So now we apply that formula in fluid mechanics in hydraulic. Okay, so we have the here. So actually this is for using the momentum force equation. Draw. Okay, draw the specific force curve. Okay, if the hydraulic jump. So using this formula, so you must take the y here in the column y here and just find the f here based on the value of it. Okay, so now so after this class, so you try to do this graph here based on SI unit, okay, using the meter cubic per second. So now you just follow there. Okay, so after you just put the y here and get the f, so you just draw the graph here based on the graph paper. Okay, so you just draw here and then you get the f minimum. Actually the f minimum at the peak here, okay, at the peak of the parabolic curve here, so you get the f minimum. Okay, and the f minimum, so you get the yc. So the yc is occur at the peak of this parabolic curve here, and you get the f minimum. So y1 and y2 with the same f are conjugate depth. Okay, and so to get the, if you get the y1, okay, so this is maybe, so the, okay, at the same f, okay, at the same f here, okay, so you get the y1, okay, you get the y2 here. Okay, so you get y1 and y2 with the same f here. The f are called conjugate depth. Okay, so conjugate depth equation from the momentum equation of the flow in a rectangular channel. Okay, so we use the momentum formula here. Okay, in rectangular channel, so you rearrange the formula here until you get the value here. Okay, rearranging from this one to this one to this one and to this one. Okay, and then it can be seen that front number can be introduced in front number power of 2, you get the q squared over gy here. So you get the front number here. Okay, so based on the conjugate depth here, so this is the conjugate depth here, so you get until you get the this one. Okay, so this is the conjugate depth. Okay, so this is called the conjugate depth. So you, so don't worry about this one. So all the formula is given. Okay, so this is the conjugate depth. Okay, to get the y1, y2. Okay, okay, so you solve the y2 and y1 here to get the y1 and y2 based on this formula. Okay, so since y1 and y2 are positive values. Okay, so else if division is made by y2 power of 3, so you get the here. Okay, so y1 over y2, so the front number 2 here, so you get the negative here. Okay, if division is made by y2 here, so you get, okay, so all the formula is given. Okay, no need to worry. So note that for hydraulic jump to occur, y2 over y1 must more than 1, or y1 over y2 is less than 1. So you must consider for this. Okay, consider for this assumption here that hydraulic jump is occur. Okay, based on the y1 over y2 is less than 1, y2 over y1 is more than 1. So this is the assumption that hydraulic jump is occur. Okay, and you must follow the conjugate depth also, okay, to get the y1 and y2. Okay, now we look at the energy losses here. Okay, there will be considerable loss of energy in hydraulic jump between section 1 and section 2. This is a section 1, this is the section 2. So in section 1, so we get the y1, okay, supercritical. Okay, when the hydraulic jump occur here, so we get the yc, the critical depth. And then after the hydraulic jump, so we get the y2 is subcritical. Okay, before the jump, so we get the y1. Okay, after the jump, so we get the y2, and hydraulic jump, so we get the yc, the y critical. Okay, so based on the energy losses is calculated as the, okay, so this is the formula. Okay, formula for the energy losses. Okay, so energy losses, okay, all these formula is also given. Okay, so energy losses to calculate el is energy losses. So this is the formula for rectangular, so this is all the all channel. Okay, for rectangular channel, it can be simplified as here. So this is the for rectangular channel. Okay, so this is for rectangular channel. So you get the rectangular channel. For all channel, you must use this one. Okay, so all channel you must do using the energy losses here. Okay, for rectangular channel, you use this formula. Okay, power due to energy losses. So this is the formula for power losses in unit watt. Okay, so height of jump. So height of jump is Hj is equal to y2 minus by y1. Okay, so this is height of jump. Okay, and the length of jump. So you use this formula. Okay, when the front number is less than 4. Sorry, 5. Okay, less and same as 5. And if the front number is more than 5, so you use this formula. Okay, so this is the formula for length of jump. So all this formula is given, so no need to worry. Okay, now look at the example here, activity 4.2. Okay, a spillway discharge flow at a rate of 7.75 meter cubic per second per meter. At the downstream horizontal apron, the depth of flow was found to be 0.5 meter. What tailwater depth is needed to form a hydraulic jump? Okay, if a jump is formed, find its type, okay, length, head loss, and energy losses as a percentage of the initial energy. So they have the step by step, okay, to find the type of jump, okay, to find the length of jump, to find the head loss and energy losses. Now look at the here. Okay, first the given Q here, 7.75 meter cubic per second per meter, and Y1 the given here. Okay, the data given here. Okay, and first you must find the front number. Okay, front number 1 here. So you're using the Q here and divide by Q, GY3 here. Okay, so use this formula. Okay, actually this formula is given. Okay, no need to worry. Okay, put all the data here, the unit, the value here, and until you get the front number 1 is 9.6.99. Okay, or 7. Okay, so maybe, okay, you get this. So utilizing the conjugate depth equation, so using the conjugate depth, okay, because this is based on spillway. So when the spillway, so this is based on the rectangular. Okay, so you get the conjugate depth equation. Okay, so you use this formula here, y2 over y1. Okay, because the y1 is given. Okay, that's why you must using this equation that y2 is at above here, because you want to find the y2. Okay, using this formula, you just put all the value here and you get the y2. Okay, so based on the front number, based on 6.999, so the jump is a steady jump. Okay, because the front number is between this range, so this is the steady jump. Okay, so the type of jump is a steady jump. Okay, now we look at the length of jump. Okay, we get the front number now, and 6.999 is more than 5. So we use this formula. Okay, this formula to get the length of jump. Okay, 6.1 times by the y2. So you get the y2 is 4.705. So you get the length of jump is 28.7 meter. Okay, so now using the head losses is given the formula here. Okay, so you just put all the value here until you get the energy losses. So the head loss is 7.901 meter. Okay, now we look at the initial total energy. Okay, so initial total energy is E naught. Okay, based on this equation. Okay, so you must remember this one. They have the step by step. So E naught here, Y1 plus Q2 Q squared over 2GY1 squared here. Okay, you just put the Y1 here, you put the Q here and the Y1 here. Okay, because you want to find the total energy before the jump. Okay, so that's why you must use the Y1. So this is based on before the jump. Okay, so you get the 12.745 meter. Okay, so after you get the initial total energy, so you must EL here is the head loss of the jump. So you get the 7.901. Okay, and divide by E naught and times by 10%. So you get the 61.99% or 62. So you get the 62% of percentage of energy losses. So this is the step by step. Actually, this is more on previous slide. Previous question for final exam. Okay, so this is then the step by step, so you must look at the step by step to get the calculation, okay, to get the value. Okay, now we look at activity 4.3 here. Okay, so a 25-meter wide spillway is discharging flow with velocity of 30 meter per second at a depth of 1 meter. Hydraulic jump. Okay, so this mentioned here, hydraulic jump occur immediately downstream. Okay, find the height of jump and power loss due to the jump. Okay, so the given B is 25 meter. Is so they have the white here, the B is the rectangular, so you get the for the rectangular, so you can use the conjugate depth here. Okay, okay, y1 is given as 1 meter here. Okay, and the v1 is 30 meter per second, so they're given the data here, so you must find the Froude number. Okay, Froude number based on this formula, so you get the value of Froude number is 9.578. okay, you get the Froude number. Then you must find the conjugate depth, okay, because you want to find the y2. Okay, the y1 is given, so you want find the y2 after the jump, because this mentioned here the hydraulic jump occur immediately downstream, so you must find the y2. The 1 2 is actually for at the downstream, so that's why you must find the y2. Okay, using the conjugate depth, so you find the y2 here, 13.055 meter. Okay, and then you find the height of jump. So height of jump using this formula, y2 minus by y1, so you get the value here, so you get the value of 12.055 meter. Okay, so using the formula of energy loss, so you get the EL here based on the energy loss here. Okay, and put all the data here and value here, and you get the EL is 28.019 meter. So using the power due to energy losses, so you use this formula to get the powers. Just put all the value here until you get the power of hydraulic jump is 206.15 megawatt. So this is in unit watt because this is power. Okay, power due to energy loss. Okay, so now we look at the gradually varied flow. Okay, so gradually varied flow, hydraulic jump is rapidly varied flow. Now we look at the gradually varied flow. Okay, a gradually varied flow is a steady non-uniform flow in a prismatic channel with gradual change in its flow surface elevation. Okay, so this is steady non-uniform flow. Okay, so example here for the gradually varied flow, so drawdown produced by sudden change based on the mild slope here and then the steep slope, so they have the sudden change in channel bed slope. Okay, based on the mild slope to the steep slope, so they have the gradually varied flow, steady non-uniform flow. Okay, based on the mild slope, so we get the M here, the symbol of M, mild slope, and the S is the steep slope. So they have the control section here, so they have the drawdown produced by sudden change in channel bed slopes. Okay, this is the backwater produced by increase in bed elevation. So in case in your final ask you to explain and list down about the gradually varied flow, so you can list down the example of gradually varied flow. So you can mention here backwater produced by increase in bed elevation. So maybe you can sketch. Okay, maybe the question asks you to explain briefly the gradually varied flow and sketch the diagram. So you can sketch the diagram and also the example, okay, the list of the gradually varied flow. So this is based on the my slope. So my slope is M1 here, and the minor slope here based on the YC and so on to the leg controls. They have the two control section, okay, based on the control section 1 here and control section 2 here. Okay, so the types of slope. So the gradually varied flow, they have the type here using the Y0 and S0. Okay, so in chapter 3, so you have learned more on about the constriction and also the broad-waisted weir, that you must know that Y0, YC and so on. Okay, now look at the gradually varied flow. You must know about the Y0 and YC and S0 also. Okay, so the type of slope based on this symbol here, M for the mild, S for the steep, C for the critical, H for the horizontal, and A for adverse. Okay, actually adverse and horizontal is not usually used. Okay, but for the real situation, so we can find the horizontal and adverse. Okay, but for this syllabus, so we just learn about the mild, steep, and critical. Okay, so the types of slope. Okay, the classification of GVF profile here based on the region 1, region 2, and region 3. So they have the 3 region. Okay, they have the channel, mild slope, steep slope channels, critical slope, horizontal, and adverse slope. And also we have the region. Okay, mild slope, steep slope, and critical slope. Mild slope and steep slope, they have 3 region. Okay, critical slope only 2 region, region 1 and region 3. And horizontal bed just only have region 2, region 3, and also the adverse slope. Okay, so this is based on this condition here, based on the type of M1, M2, M3, S1, S2, S3, C1, C3, H2, H3, and A2 and A3. So this is the type of the mild slope. Okay, so when you see that when you see that M1 here, so this is mean that mild slope in region 1. Okay, M2 is mild slope in region 2. Okay, mild slope in region 3, and so on. Okay, so that's why when you look at this graph here, so you know that the M1 here is the mild slope at the region 1. Okay, and also this space here, so M2 is the mild slope in region 2, and S2 is also steep slope in region 2. Okay, so this is based on this symbol. Okay, so now we look at the classification also. So actually this is classification of GVF profile based on this condition. Based on this condition, so can draw the diagram here. Okay, based on the region 1, region 2, and region 3. Okay, the mild slope, mild M, they have the region 1, region 2, and region 3. The Y more than Y naught and more than YC. Region 2, Y naught is more than Y and more than YC. Region 3, Y naught more than YC and more than Y. Okay, so this is based on the region. Okay, the steep, so you must also use this one. But for the critical, just only have the region 1 and the region 3. Okay, critical just only region 1 and region 3, no region 2. Okay, and the horizontal just only have region 2 and region 3, and also the adverse is also region 2 and region 3. Okay, all curve in region 1 have positive slope, so the backwater curve. So all curve in region 2 have negative slope, so this is called the drawdown curve. Okay, so in case your final asks you explain based on your opinion, okay, based on the diagram here, so you can explain what. Okay, maybe at the region 1, okay, the positive slope is backwater curve, so region 2 have negative slope is drawdown curve, so you can explain based on this diagram. Okay, so this is the y slope. Okay, based on the diagram the previous slide that I give to you. Okay, this is the based on from the reference book. Okay, this is based on the as the mentioned from the previous slide. Okay, so you look at the occurrence of flow profile here. Okay, so M1 profile, so this is based on the region 1, mild slope at the region 1, M1 profile. Okay, occur due to obstruction to subcritical flow, example as weir, dam, or other control structure. So the profile extend to several kilometers upstream before approaching the normal depth. So we know that Y more than Y naught more than YC, this is M1 here, mild slope. Okay, this is the M1 profile. Okay, the M2 profile occurs when there is a sudden drop. They have the sudden drop here in the bottom of the channel, constriction of channel or channel outlet into reservoir. So this is also maybe the sudden drop here. Okay, M2. Okay, and the M3 profile is occur when supercritical flow enters a mild slope channel, flow from a spillway or sluice gate to a mild slope. So maybe in this case, in your final ask you to explain briefly about M3 profile and sketch the diagram. So maybe you can define the M3 profile and you sketch the diagram. Okay, occurs when supercritical flow enters a mild slope channel example of flow from a spillway. This is a spillway or a sluice gate to a mine channel. Okay, from the sluice gate or spillway, they have the mine slope here. They have the YC and the Y naught here. Okay, so this is M3 profile. Okay, this is S1 profile, occurs when subcritical flow change to pool of water, subcritical flow due to obstructions such as weir or dam. Okay, so this is the S1 profile. This is S2 profile, occur when flow from reservoir enter a steep slope or when there is a change from mild slope to steep slope. So this is the S2 profile, and this is the S3 profile here based on the steep slope, steeper slope, and okay. So this profile is of shorter length. Okay, so this is for S3 profile. So the C1 and C3 profile is highly unstable and rarely occur. So this is based on this. Okay, this condition. H2 and H3 profile is occur when the bed of mild slope become flattest. So become the flattest here. There is no region 1. So since Y0 is infinity. Okay, so no region 1. So the since Y0 is infinity. So this is concept of H2 and H3. Okay, maybe in your final they give you the diagram here, so you explain what is the condition of this diagram or this figure. So you can mention about the H2 and H3 profile. Okay, so this is based on the question. Okay, so the A2 and A3 profile is occurs when flow is on adverse slope. When adverse slope here, okay, which is rare. This profile occurs within a short length. So D and E is actually the happen in real situation, in maybe in river, maybe in the sea and so on. Okay, so this is actually this is rare. Okay, which is rare. So occurs when flow is an adverse slope, so which is rare. So this profile occurs within a short length. Okay, so you can explain. Now the example here for point 4 here, determine the type of profile for the following flow. So this is that I mean, okay, if in your final or okay, give you this figure here, so what you can explain based on this figure. Okay, and also this figure. So this is the sluice gate. Okay, and why is not here and why C here? So this is what. So you can explain based on the YC more than what YC is more than Y not. So this is the S. Okay, at the zone 1 here. Okay, and zone 3 is the S3 here. So this is the sluice gate. So you can explain based on this profile, and the sluice gate is based Y not more than YC. Okay, so you get the M here. Okay, at the zone 1 is M1 here, and the M3 is the zone 3. So you can explain here. Okay, so based on this situation. Okay, activity 4.5 here, a rectangular channel with bottom width 4 meter and bottom slope 0.0008 has discharge of 1.5 meter cubic per second. Along the gradually vary flow in the channel, the depth at a section is found to be 0.3. Assuming that magnitude and 0.016, determine the type of GVF profile. So the mean here, you must find the type of GVF, gradually vary flow profile. Okay, first you must use that this is rectangular section. So B is given as 4 meter, S naught is 0.0008, and N 0.016, Q is here 1.5 meter cubic per second, and Y is 0.3. Okay, so you must find the Y naught first. Okay, because they give you the Y here, so they give you the depth of section. Okay, along the gradually vary flow in the channel, the depth at a section, okay, is found to be 0.3 meters. So give you the Y here. Okay, so you must find the Y naught first. Okay, to get the Y naught, because you want to find the profile of that type here, GVF profile. So you must find the Y naught. So Y naught, you must find the Y naught based on the formula here in chapter 2. Okay, to get the normal depth. Okay, Y naught is normal depth. So you must refer to the chapter 2. Okay, so you get the Y naught based on the try and error or so on. So you get the Y naught here. Okay, so now you get the YC. Okay, so step 2, you must find the YC. So YC is based on the rectangular section. So use the Q here based on the B. So you get the YC is 0.2429. Okay, so you get the value here Okay, so the YC y naught is more than y is 0.3, so y naught is 0.4, so y naught more than y, and the y is more than yc. So based on this profile. Okay, so you get the M2 profile. Okay, so now activity 4.6 is also the same. Okay, determine the type of loop and give the limit of depth of loop in region 1, 2, and 3. Okay, triangular. This is using the triangular channel. Okay, so using the triangular channel, you know that the Z is 1. So F naught is 0.001 and Q here. So you must find the Y naught first. Okay, using the formula to get the Y naught. Okay, to get the Y naught is based on the formula that you have learned in chapter 2. Okay, so you get the value of Y naught. Okay, after you get the value of Y naught, okay, then you find the using here to get the YC. Okay, this is based on the all section because you use the triangular section, so you must use this formula. Okay, refer also to the chapter 2. Okay, so you find here and you get the YC. Okay, so you get the Y naught is more than YC. Okay, so this is my slope M. Okay, and for M1, okay, y is 0.5361 meter. For M2, so this is based on this concept, and the M3 is this one. So you can also using this type here. Okay, actually this is to find the give the limit of depth. Okay, so you find the region 1, 2, and 3. Okay, after you get the mile slope here, so you just give the limit M1, M2, and M3. So based on this condition. Okay, so this is okay, that's all to be continued in part B. Assalamualaikum warahmatullahi wabarakatuh.